Hello, my name is William Hale. I teach at a large high school in Fayetteville, North Carolina. I teach both chemistry and physics. Today I am here to talk to you about entropy. As we well know, entropy has to deal with the random motion of particles. And today I'm going to be trying to talk to you about that and use a few examples as our assignment was stating. The first thing we need to know about is what is entropy, and I'm going to only give you a layman's term, a way to describe entropy. Entropy is something where you've got things moving quickly or chaotically or randomly, maybe not quickly, but random, chaotic movement. And that's kind of the way that we kind of teach what it is. If you look up on the board there, I have several different things up there. This is my smart board, by the way. Let me get my stick here. We have these capital S's. This is a small capital S. That stands for entropy. Delta S would be the change in entropy, but since it's not changing, hopefully we won't be doing those calculations. Then it's capital S, middle-sized capital S for more entropy, and the largest S for a greater entropy. So that's kind of the way I want to look at this here. Then you have four words on the top. You have puzzle, then you have ice, BBB, and BBT. We're going to go through this in each order, then I'm going to have you practice your ABCs. We're going to find out what's behind each of these doors, A, B, C, and D, E, F, G, and H, so we can practice those. But first of all, let's look at the word puzzle. We see the word puzzle, P-U-Z-Z-L-E, right? P-U-Z-Z-L-E. Small entropy. In other words, that's what it's supposed to be. It's a puzzle. So it's perfectly where it's supposed to be at. No chaos there. But let's find out what it's going to look like if you take open up door number A. Now you have a puzzle that's kind of messed up a little bit. It's uzzle with a P and an E on the bottom there. Look. Uzzle, P and E. It's a little bit more chaotic than this. You might still be able to tell that's a puzzle, but it kind of looks a little bit strange. So now it has some more entropy there because there's more randomness to it. Let's look what's under door B. B is just a bunch of letters piled there. Therefore, it has more entropy. Puzzle has more entropy. So puzzle starts here with a small capital S, then a larger capital S because there's more chaos here in the letters. And here has the greatest chaos in the letters, so therefore it has the greatest entropy. Let's cover up those so we won't have to worry about them. The next category, as you can see, is ice, and I bet we can guess what this is going to talk about. Ice. Ice is a hard piece. Ooh, I forgot to bring my ice. We'll just pretend this one here. We know what a piece of ice looks like. A piece of ice is just a solid piece. You could actually measure the sides and multiply those sides apart to get the centimeters cubed, or you could take the ice cube and put it into a graduated cylinder, push it underneath, find out how much the volume of the water comes up, so you can come up with the volume. A solid has a definite shape and a definite volume, whereas ice has a definite shape and a definite volume, but so therefore it has less entropy. We're going down to a liquid. Oops. On door number C, letter C, water. What do we see? Definite volume, but no real definite shape. Water. So therefore it has more entropy. Ice, water. Now I bet we can guess what this last one's going to be. Of course it's going to be gas or steam. Steam. I brought in my Dexter cup from though I didn't, I brought a different cup, sorry. But you can see the steam if you take a look closely. Just watch it rise. There's the steam. See how the steam rises? Its steam is rising and moving randomly. So therefore, the steam has a greater amount of entropy. Solid, ice, liquid, and gas. In the classroom, a lot of times I'll talk about the maybe some perfume that's in the room, and it's liquid over in the bottle, but eventually it spreads all over by its chaotic movement all over the room. Let's cover up C and D again. I'll have to speed up a little bit here. Next is BBB. Here we're a little bit more on the peripheral of the topic. BBB, that stands for a big brown bear. Big brown bear. Then it's got question marks here. We're going to try to tie this into biology a little bit. And I haven't had a biology class since 1978, so just forgive me. We have random mutations that happen so often. Sometimes, most of the time, they don't affect the organism one way or another. Sometimes they're detrimental, sometimes they're good. We know about 150,000 years ago there was a major ice age. So therefore, some of the big brown bears were way in the north, and they were too cold for them. That wasn't as good of an environment as it should be. So some of them mutated, and maybe became a little bit lighter, heavier, bigger animals, and more able to move around, maybe not dexterous, I can't think of the word right now, but able to move and be more, be able to catch prey at a quicker pace if they needed to, and also lighter and larger. So they eventually came back to become the underscore F, which is the big white bear, the big polar bear. They eventually changed into a big white bear because you had these incremental chaotic changes, which just so happened to change to a big white bear or a polar bear. It's chaotic as far as for a big brown bear, but it's not for the big white bear. Therefore, it could actually go in reverse order. I'm not saying you create a big brown bear out of a big white bear, or you can't produce a grizzly bear out of a polar bear, but it could go back in the opposite direction if it got warmer. So let's cover up those two. Now we've got another peripheral idea. G and H. Top it says BBT. That's a Big Bang Theory. Boom, that explosion. It exploded. What happened? The particles all started moving out in all directions. If you know anything about physics, collision, all the directions of the particles, you add all these speeds together, all that momentum together in all different directions, you add them together, it comes up to a zero. And no movement, no work is being done because there's no particle movement. All of them cancel each other out. But we continue on with this. But we know that doesn't really happen. The universe is continually getting larger. The universe is infinitely large, but the particles can't get further and further. But we know also that there is some containment to this increase as well, because you have the planet Jupiter, for example, so large. Maybe a meteor is coming by and you get stuck into the gravitational attraction by a large planet or what have you. So it's not really that complete pull out. In this class, though, what I would have the students do, I would give this topic to them. We would cover the actual definition itself, but I would have the students in groups of 3 come up with an idea for themselves, and then they can present it to the class. Well, hopefully that helps you understand a little bit about entropy. I'm trying to make it a little bit simple for us, but hopefully that'll help you. Thank you very much. Take care. Let's see. Sorry about that. I'm not good at this.